Good evening, good morning, or good afternoon, everyone, wherever you find yourself watching this video. My name is Pietro Shanika, and I'm going to present to you a subsection of the project that my colleague and I have been doing here at the University of Namibia. And my colleagues' names are Linus Njala and Dr. Hans Renate. So when I submitted my abstract, the title was the antimicrobial and antibiofilm activity of Chalcones modified using the Povarov multi-component reaction. However, I made some changes to it, and this is the new title that I'm going to work with going forward with this presentation. And that is the Chalcones modified using Povarov multi-component reaction as potential antimicrobial agent. So to start off with, the overview of this presentation, I will look at the introduction, objective of this research, the methods that we used, results, as well as then future recommendations that can try to improve this project. To start off, the WHO declared antimicrobial resistance is one of the top 10 that is threatening the public health sector. And it is estimated that by 2050, there will be 10 million deaths 10 million deaths annually that is related to antimicrobial resistance. Because of this, there is a need for us to come up with new drugs that are novel, that are at least to address this antimicrobial resistance. And fortunately enough, one of the ways which we can address this antimicrobial resistance is to try to come up with drugs that are inspired or from natural product. The reason for this is because nature has been shown that it has scaffolds that are diverse and their structure is complex. Furthermore, it is also reported in literature that natural products and their derivatives are already in the market as drugs, for example, as antivirals, antibiotics, as well as anti-tumor drugs. However, unmodified natural products always have issues, and one of them is the issue of pharmacokinetics, that is, unmet properties which are not suboptimal for drug use. And these unmet properties are basically the abbreviation standing for absorption, distribution, metabolism, excretion, and toxicity. So in our project, we are then trying to look at the Chalcones derivatives. Since this Chalcones framework is a privileged natural product scaffold due to its broad spectrum biological activities. And this biological activity ranges from anti-cancer, anti-inflammatory, antimicrobial, as antiviral as well. And this is the structure of generic structure of a Chalcone. And the reason why this Chalcone show this broad spectrum and biological activity is because of the alpha beta unsaturated ketone, which is that. And for us to then try to optimize these structures. However, even though these natural products show these promising activities or have this broad spectrum biological activities, there is a need for them to be optimized in terms of unmet properties. So that's why then synthesis comes in to try to optimize these natural product scaffolds or these privileged natural product scaffolds. And one of the ways that it can be achieved is using a multi-component reaction, which offer various advantages over a stepwise linear synthesis. For example, in terms of atom economy, in terms of time, as well as in terms of the number of steps that you need to do purification. And one of these examples of this multi-component reaction is what we call a Povarov reaction. And the Povarov reaction ends up producing nitrogen-containing heterocyclic compounds, such as the tetrahydroquinoline scaffold. And this is the scaffold of the tetrahydroquinoline. And for a drug molecule to be approved, for a drug candidate to be approved as a drug, it has to be active, first of all, and secondly, it has to have favorable ADMET properties. And because of this, we can reduce the attrition rate of the drug discovery and development process by trying to evaluate these ADMET properties as early as possible in the drug discovery and development stages. And there are various uh, servers or platforms in which we can evaluate these ADMET properties, such as the Swiss ADME, the ADMET SAR, More Inspiration. All these are some of the platforms that can be used, and each of these platforms has its own different parameters that it can predict. Even though these platforms have their own advantages, there are two limitations that I would like to highlight. The first one is that some of these platforms, they don't have a privacy issue. And second limitation that I would like to mention is that even though we are able to predict these parameters, these ADMET parameters, it's possible that these ADMET profiles might not correlate to in vivo or in vitro biological data. So it's always good to remember that these ADMET parameters through these servers is just predictions. Okay. So one of the other way also to lower the attrition rate of the drug discovery and development process is by doing docking. And the reason why we do docking is that because it's a cost-effective approach before we are able to do in vitro assays, because we are able to predict the binding affinity and show the ligand receptor interactions, which might help us to predict as to which compounds to synthesize and take further for in vitro as well as in vivo assays. Because of that, then the objective of our project is that we want to perform in silico guided design as well as do docking studies of novel Chalcone tetrahydroquinoline adducts. And this is the scaffold of the tetrahydroquinoline adducts. And then after the design, we would like to do the synthesis, characterization, and then finally test the antimicrobial activity of these synthesized adducts. In terms of then the research design is that the first thing is that we'll do the design, or we did the design of these adducts, and then we did the in silico profiling, and then we did the docking studies. And then after the docking study, we realized that some of these compounds need to be optimized further. That's why we had to redesign further other compounds for in silico profiling as well. And then after that, we then nominated a short list of some compounds that we submitted for synthesis as well as characterization, which will then be taken for antimicrobial screening. In terms of method, for the design, as I mentioned, we used literature data as well as existing SAR in the literatures. And then for the in silico, we did to predict the ADMET as well as the physicochemical and drug likeness. We used the Swiss ADME as well as the ADMET lab. And then for the docking, we did the docking against two enzymes. The first one is the lactamase, the New Delhi metallo beta lactamase, which is an enzyme responsible for hydrolyzing drugs and which at the end of the day results into drug resistance. And the second enzyme is the DNA gyrase, and the DNA gyrase is only found in the bacteria, not in the human host. And because of that, we can pick this DNA gyrase as it is responsible for maintaining the DNA topology during DNA replication. And when we did the docking, we used two reference compounds. The first one for the lactamase is the indole derivative, while for the DNA gyrase, we used a quinoline derivative. And then in terms of geometric optimization, we use ChemDraw Autodoc tool as well as Chimera X. And then the CAST-P, we used it to predict the binding site of these two enzymes. And then after that, then we did the docking, the visualization as well as the analysis of the docking and then the binding using Autodoc Vina of the Pyrex as well as Discovery Studio. For the synthesis, this is the generic structure of how we did our synthesis. In terms of the Chalcone, we synthesized it using a Claisen-Smith condensation, while for the THQ adduct, we use a Povarov multi-component reaction, which in other words, it's called an azadiyls-aldehyde reaction. And then in terms of the antimicrobial, it will be tested against the escape pathogens. And these escape pathogens are these that includes both gram-negative as well as gram-positive. And these bacteria are shortlisted by WHO as a high priority because of antimicrobial resistance and because of the lack of drug that can be used to treat these bacteria species. So the antimicrobial will be done using this diffusion method as well as the MIC, and the MIC will be evaluated using the standard broth microdilution method using gentamicin as a positive control. So in terms of then the results, what we got in terms of the design is that we got 180 THQ adducts with varying aldehyde of the Chalcone and varying the aniline that was used in the Pavlov reaction. And again, the R there was varied in terms of either a hydrogen or a hydroxyl. And that R group is part of the acetophenon that was used for the Chalcone synthesis. The criteria that we used in terms of designing these adducts was that first, we looked at the literature data, what is available in the literature, and what is the different SR groups that can be introduced for Chalcone. The other part is that we did the in silico screening, which gave us an idea of which compounds to synthesize or which adduct to synthesize. And in terms of substituents on the different aldehydes as well as the anilines, we tried to cover all four quadrants of the Craig plot. And then the last two aspects that we looked at when it came to the design is that our adducts should have more heteroatoms as well as few rotatable bonds because most antibiotics has been shown that they have more heteroatoms as well as few rotatable bonds. Then in terms of result of the in silico, we did the in silico using two servers, that's the Swiss ADME as well as the ADMET lab. And what we found out is that these two servers, in terms of the results, is comparable. The only highlight that needs to be highlighted here is that for the Swiss, in terms of the hydrogen bond acceptors, they say that aniline is neither a hydrogen acceptor nor a hydrogen donor. That's why then we see a difference that in the Swiss there is 1 to 7 hydrogen acceptors in terms of the range for all our compounds, while for the ADMET lab they were between 2 and 9. That's the variation. Other than that, the total polar surface area or the TPSA, they are comparable, log P comparable, and then the other aspect that I needed to highlight is the triple B, which stands for polar surface area, brain blood barrier, which is just a membrane that prevents molecules passing to the central nervous system. For the Swiss, it's predicted that there were only 552 compounds from our 180 that passes through the triple B, while for the ADMET, there were only 62. And then the last aspect is that for the paints, for the Swiss, there were 24 paints that were flagged. For the ADMET lab, there were only 12 paints that were flagged. In simpler terms, paints are basically pen assay interference compounds, which are then able to give false positive when you're doing in vitro or in vivo assays. So as much as possible, we want to get rid of these paints molecules from the start of the drug discovery and development project. So in terms of then our filters that we applied in the in silico to limit the number of compounds that we are working with. So the filters were that we applied the Limpinski rule of 5, and then we also looked at the glycoprotein influx transporters that our compounds should at least inhibit this glycoprotein influx, because these are the ones that are responsible to transport our compounds out of the cells. And then we looked at the triple B, that our compound should not permeate through the triple B, and that our compound should be stable in the human liver microsome, or the HLM, and that it should at least have a reasonable clearance, plasma clearance, and that they shouldn't be Heg blockers. And Heg blockers is in this case are very important, because the Heg is a gene that is responsible for the transportation of potassium in the heart. So if you are able to block these genes, that means that the patient can go into cardiac arrest, and then that is not a good thing for drug discovery and development. And then the last aspect that we looked at is that our compound shouldn't be carcinogenic. And again, this is the THQ that we looked at. And after we applied all these filters to our 180 compounds, we only managed to get 16 compounds that fit all these parameters. So when we look at the physiochemical properties, we see that in terms of molecular weight, hydrogen acceptor, hydrogen donors, hydrogen bond donors, log P, they all obey the Limpinski rule of 5, which is less than 500, less than 10, less than 5, as well as less than 5 in terms of log P. And we found that the total polar surface area of these 16 compounds ranged from at least 62, around 62 to around 108. And I have to mention that in terms of total polar surface area, is that it advised that it should be between 90 and 140 for it to be oral available. Anything above that is not orally bioavailable. And if it's less than 90, then that means that that compound is able to permeate through the triple B. And this is clearly what we see, that all our compounds except compound number 10, 11, and 12 are the only ones that are not able to permeate through the triple B. In terms of P-glycoprotein inhibitions, all our compounds were not able to inhibit these glycoproteins. And then in terms of synthesis, all our 16 compounds can easily be synthesized. And then in terms of fraction of sp3, this fraction sp3 is directly related to solubility. And in terms of our compounds, all the sp3 is really very low. So again, it's possible that we might have issues with solubility. And then the last aspect that I also wanted to mention here as well is that since we have low total polar surface areas, it could also mean that all these compounds will easily be excreted out through urine. And then the other aspect that we looked at is the metabolism, excretion, and toxicity. In this case, in terms of the CYP enzymes inhibition, these enzymes, the CYP2D6 and the 3A4, are found in the liver, and they are responsible for the metabolizing the drug candidate during the phase 1 metabolism. And in terms of the 2D6, only compound number 16 was able to inhibit it, while for the 3A4, all our compounds are able to inhibit those enzymes. In terms of human liver macrosomes, only have to highlight is that only compound number 3, 5, and 6 have a low stability in the human liver macrosome. And then in terms of plasma clearance, we found that at least our compounds are they have excellent stability. Let me just put it that way, they have excellent stability. And then in terms of half-life, unfortunately, all these 16 compounds have ultra short half-life, except compound number 11 that at least have a a half-life of over an hour. The rest, their half-life is below an hour. And again, all our compounds are are inhibitor of Heg moderately because the inhibition is around 60%. And the second last aspect is that in terms of DILI, and this DILI stands for drug-induced liver injury, we found that most of our compounds are not able to induce liver injuries except compound number 13. And then finally, all our compounds are not carcinogenic except compound number 4 that has a probability of being carcinogenic at 69%. And then in terms of docking results, remember I said that we did the docking against two enzymes. The first one, the 6NY7, is the lactamase enzyme, which is responsible for metabolizing drugs, and at the end of the day results into drug resistance. We found that only 3 compounds showed at least better or reasonable or higher binding affinities, which is -7.7, which is higher than our reference compound, which is at -6.3. And these are the 3 structures of those compounds that had better binding activity, and that is the reference compound, which is the quinoline reference compound. And for the second enzyme, which is then the DNA gyrase, we found that it's only compound number 11 that really showed good activity, which is almost twofold the reference compound. And this is the structure of compound number 11, and this is the reference, which is the indole reference compound. So in terms of docking interactions, when we look at the lactamase enzyme interactions between compound number 4 as well as the reference compound, what we see that there is a lot of unfavorable bumps. And these unfavorable bumps, it's an indication that the conformation of our ligand is not compatible with our binding sites. And therefore, there will be an unlikely binding to the protein with high affinity. So hence, there is a need to do a follow-up study that can help to confirm the predicted binding energy. However, for compound number 4, we see that there is an additional hydrogen bonding, which might explain as to why we are seeing at least a better binding energy for compound number 4 as compared to our reference compound. And then in terms of the DNA gyrase enzyme, and again, we saw that it's compound number 11 that produce the best binding energy which is at 8.2, -8.2, which is almost 2 folds better than the reference. And in terms of, again, binding interactions, we see that we still, again, find the unfavorable bumps. However, we also, again, see hydrogen bonding in our compound number 11, which we don't see in compound number, in our reference compound. And the other aspect also is that in terms of the binding distances, in our compound number 11, the binding distance are at least a little bit shorter compared to that of our reference compound, which might explain as to why we see a better binding energy. And then the other aspect is in terms of synthesis. The first aspect was the synthesis of the chalcone, which we did through the Classen-Smith condensation, and we produced our chalcone using different acetophenone as well as aldehyde derivatives with a yield of 25 to 71%. And then we carried out the chalcone through a Povarov reaction using an aniline and aldehyde, and we obtained our THQ at the yield of 19 to 150%. Then the way forward for our project is that we would like to do, the first aspect that we would like to do is we would like to do a further docking, and that will also involve molecular dynamics where we try to do the simulations to check the interactions between the atoms as well as the the atoms and the binding sites over time. And we would also like to do the reverse docking as well as the meta site predictions for us to know what are possible lead compounds as well as the metabolic weak points of these lead compounds. And then we would like to complete our synthesis and as well as characterization. And then finally perform the antimicrobial activity testing and then relate these antimicrobial activities to their in silico results that we got. That brings me to the end of my presentation. Thank you very much, everyone, for watching my talk. Enjoy the conference, and here are the details of the email address of all the research team members if you would like to get a hold of us. Thank you very much. Have a good day. Goodbye.